Let's talk about force equations. Force equations are going to be the best way to try to solve force problems now that we are trying to put some numbers to all of this stuff. So first, let's review what it really means to have balanced forces. We know that we have balanced forces when an object is at rest or moving at a constant velocity, but what does it really mean? Well, what it's really trying to describe to you is that any kind of forces that are pulling maybe to the right have to be equal to the forces that are pulling to the left. That would be balanced forces in the x direction. Same thing with the y direction. Forces pulling up are going to have to be equal to the forces that are pulling down. Now we can also write that in a very mathy way. The Greek letter sigma means sum in math, and so what we are trying to say by saying that the forces pulling right is equal to the forces pulling left is that if you sum the forces in the x direction, they should all add up to be 0. And if we sum the forces in the y direction, they should also add to be 0. That's what balanced forces really means. So let's look at a force diagram and try to look at whether or not the forces are going to sum up to be 0. So we've got a box, and we've got a person who is trying to push this box. Okay, so we are very interested in the box, so we will make the box into our system, and we will give a dot for the center of gravity of the box. So there is a box that has mass, so the force of gravity on the box by the earth. There is the floor, so there is a normal force on the box by the floor. This person is pushing the box to the right, so there must be some kind of applied force on the box by the person. And, well, this thing is sliding along the floor, so there is probably some friction on the box by the floor. Now, if we look at this, I want us to kind of imagine laying an x-axis and a y-axis onto this force diagram. So we can imagine that this is kind of like a nice x-axis, and this is a nice y-axis. And that's going to help us because I would like to try to look at the forces that are in the x direction, and I want to write a force equation to sum them all together. So again, we are trying to sum the forces in the x direction. So pointed to the right, I've got an applied force, and pointed to the left, I have a force of friction. As far as I can tell, those are the only two forces I have that are pointed right or left. So those two forces must add up to be 0. And if I look in the y direction, while it appears that the force of gravity is pulling me down, there is a normal force that is pushing me up, and there's nothing else going on in the y direction. So those two forces, when we add them together, they have to equal 0. Now we can use these wonderful force equations to help us. That's what we would call these two things. We call these force equations. Now, your force equations are going to change for every force diagram. Every force diagram has different force equations. They are certainly not worth memorizing because if you have a different force diagram, those force equations that you memorized are going to be totally worthless. So just know that we wrote them from looking at a force diagram. Now they're going to help us solve problems because perhaps I want to know what the force of normal is. Well, if I want to find that normal force, as long as I know what the force of gravity is, I can use this force equation to figure it out. So let's do that here in exercise 1. So a car of mass 1,500 kilograms is stuck in a snowdrift. Ruby pushes on the car with a force of 100 newtons, but the car doesn't budge. So let's imagine a giant snowdrift, and then we've got a car. You can make it as cartoony as you want. Now, Ruby is pushing on this, so we've got a girl. And now don't ask me why she's pushing this into the snowdrift. I have to admit, I don't know why. Maybe it's her brother's car. Her brother was being mean. But anyway, let's try to draw the force diagram for the car. So this car has mass, so there is a force of gravity that is pulling down on the car by the earth. This car is staying on the ground, so the ground must be pushing up. There is a normal force on the car by the ground. Ruby is pushing on this, so Ruby is applying a force. And then that snowbank is stopping that car from moving forward. So there must be some kind of a normal force on the car by that snow. And that's our force diagram. The car doesn't budge, so there's no slipping or sliding, so there's no friction, and there's no ropes in this, so I can't see any kind of a tension force being there. So that kind of covers all of our bases. So the first thing that we want to do is we want to write an equation that describes the forces which act on the car in the x direction. So this is asking you to write a net force equation in the x direction. If we look, Ruby is applying a force to the right, and then there is a normal force due to the snow that is pushing to the left, and that's the only left-right forces I can see. So those two things must add up to 0. Now let's write the net force equation for the y direction. There's a force of gravity on the car, and then there is a normal force due to the ground that's pushing up on the car, and those are the only up or down forces, so those things must add up to 0 as well. And then finally in part C, we want to find the normal force on the car by the snowdrift and the normal force on the car by the ground. So what are we trying to find? Let's highlight it. We're trying to find the normal force on the car by the snowdrift, and we're trying to find the normal force on the car by the ground. Now you can see that I've already got these force equations that have both of those things in it. So let's try to use these equations to help us solve for what that normal force is by the snow and the normal force by the ground. Now, if we look in the x direction, as long as we know what the applied force is, we would have everything that we need to know in order to find the normal force by the snow. And it tells us what that applied force is. It's 100 newtons. So Ruby is pushing with 100 newtons. So we will say 100 plus the normal force due to the snow has to add up to be 0. So to find out the normal forces on the snow, we subtract the 100 newtons to the other side, and the normal force due to the snow is negative 100 newtons. And that negative sign is important because that negative sign tells us that it is pushed to the left. We can do this same thing trying to find the normal force by the ground. Now, they don't directly tell us the force of gravity, but they do tell us that this car has a mass of 1,500 kilograms. Now we know that 9.8 newtons per kilogram multiplied by the mass will tell us what the force of gravity is on the object. That is the only equation that we have this unit. And since that force of gravity is pointed down, we'll add a negative sign to it. So then we add to it the normal force due to the ground, and they should add together to be 0. So to find the normal force on the ground, well, 9.8 times 1,500, I think that's 14,700 newtons plus normal force due to the ground has to add up to be 0. So the normal force due to the ground must be 14,700 newtons. There we go. We answered the question for part C. Now, this was a very simple problem, and I'm sure you guys thought that it was a bit overkill to be writing the force equations and everything like that, because the force diagram pretty clearly showed that this force had to be the same as this force, and this force had to be the same as this force. But this problem was really just to show you the process of using force equations to help you solve a problem, and we will absolutely positively need this process when we do more complicated problems. The process will always be the same. We'll always first draw the force diagram, and then we will write some force equations, and then we will use those force equations to solve whatever the problem is asking us to do. That is a foolproof method that will work on any problem that I will ever give you. So trust the process and learn it. Make it like the back of your hand, okay?